Well, hello and welcome everybody to the next episode of the Earthen video podcast. I'm Scott Howard with Earthen Natural Building. And today my guest is Lisa Morey from Colorado Earth. Welcome, Lisa.
Hey there. Thanks, Scott.
So we've been knowing each other a while now. We met through, through the grapevine, through the natural building community. And I understand that you are a licensed engineer and architectural designer working in Colorado through your company, Colorado Earth. I know you have a block making factory there, and so I'm pretty excited to get into discussing some of the nitty-gritty of creating those blocks. I'm sure our audience would love to hear about your story, about how you got to this point, being a business owner and being heavily involved in cutting edge natural materials science and natural building. So just give us a little overview, if you could, about your journey up to now.
Sure. All right. I won't take you too far back, to my Tinker Toy days. But
the first I was born.
But hey, Tinker Toys were my favorite toy. I did a lot of, probably not so sophisticated creations that my mom took lots of pictures of. But hey, I went to engineering school, got a degree in construction engineering and management back in North Carolina. At that time, I was always interested in green building, whatever the heck I could figure out what that meant. And I think what we're all still kind of trying to figure out today, even what it means. And so that led me to an art school in New Zealand, really just to explore some architectural desires and passions that I had. And I was given an assignment when I was in architecture school in New Zealand to follow a project that was under construction, document it for a year, and write a paper and maybe learn something from watching, observing, and perhaps some interviews. So my interest in green building led me to a builder on a nearby island called Waiheke, 30-minute ferry ride outside Auckland, and he was building mud brick houses. He was a builder that had been doing traditional construction until a friend in New Mexico asked him to help him out on an earthship construction project. So one of the tire houses by Mike Reynolds. And there were some Adobe aspects to the project, and that's what this builder, his name is Vince, really gravitated to, and so brought that technology back to New Zealand. So when I met up with him, he'd been doing it for about maybe 5 or 6, 7 years even, and had built many beautiful homes on the island. So I completely enamored in this process that I was seeing. I was seeing bricks being made, I was seeing walls being stacked and plastered, and sculptural elements coming out of the wall. And I just started to learn about the history and kind of our connection to this practice that dates back 10,000 years, right? And we've been in constant use of it. So I was bewildered, as I had never heard of this or seen this before, kind of in my upbringing or exposure. And of course, just saw so many benefits and seeing it all kind of come together from beginning to end, in a year, was what just really led me to kind of feel like this was the modality of work in the built environment that I wanted to pursue. So I ended up finishing, a kind of a diploma in architectural design and working with this builder. Ended up living in New Zealand for about almost 5 years, and we built houses together around the North Island of New Zealand this way. That paper that I told you about kind of turned into slowly a do-it-yourself manual for our owner builders. And then in about 2010, it was actually published as a book called Adobe Homes for All Climates. So that was kind of my, entry, my gateway, like into this obsession now with, that was back in, 1999, I moved to New Zealand. So it's, I've been practicing as an engineer also while promoting natural building and earthen masonry. Is kind of, what I've been practicing. So that's kind of how I got into it, I guess, to answer your question on New Zealand. And New Zealand, I will say a little bit more about New Zealand, is that it has probably notably the best earth building standards written in the world. So, New Mexico is kind of the standard that here in the US we use a lot. It's about, I don't know, maybe 10 or 12 pages of code. New Zealand has 3 booklets, each of which are about 100 or 120 pages each. One specifically dedicated to the materials, and the 2 others dedicated towards the engineering. It's seismic in New Zealand. It's wet. There are, certainly variety of kind of natural disasters and elements, that can influence the earthen blocks, but they've figured it out. And so it was a great training ground, really, for me, with great standards and great, engineers familiar with the practice, and a really do-it-yourself, beautiful culture also with the natural environment. So super happy having lived in New Zealand and having that kind of experience to start with.
Right. So then you moved back here, and you moved right to Colorado, isn't that right?
No. It took me a little while to figure out, where I was going to land. So I ended up coming back to Florida. So some life changes in my personal life led me back to Florida, and I started a Adobe yard in Florida, in kind of Central Florida area.
Oh, cool.
So everyone was like, I was, sit next to people or talk to people at the grocery store, I'm working with Adobe. They said, well, what part of the computer development software are you working with? And I'm like, no, not that Adobe. So there's
Adobe.
The real Adobe, there wasn't a history, there wasn't a knowledge of that type of construction in Florida, as there is so in kind of New Mexico and Arizona, and even Colorado. There's a history of it. So it took a lot of education again in Florida. However, a lot of the government, I was working with the government, and a lot of the government was buying and testing blocks from me early 2000s. So they were looking how to get a bullet through the blocks. They were looking how to get radar through the blocks. They were buying blocks and building structures and testing them at various capacities. So not exactly what I, signed up for or thought I would get involved in, but that was the majority of the work at that time. Another change of life circumstances brought me to the Pacific Northwest, where I was in Seattle and then eventually Vancouver, British Columbia for about 6 years. There I practiced as an engineer and kind of, whipped out that engineering degree and, learned a lot of transportation, civil, more like civil work.
Right, civil. Okay.
Yeah. So multidisciplined, a lot of project management skills, a lot of, design, deliverables, risk analysis. I mean, just the whole kind of umbrella design build, a large design build project. So I sharpened my skills on just delivery of projects, scope of work, schedules, budgets. But meanwhile, giving talks at universities about this type of construction, earthen masonry, connecting with a professor there at UBC on seismic design, doing workshops at a farm, building ovens, and, just couldn't get my hands out of the mud, I guess, right? And knew that this was something, I was raising a family, but this was something that I was wanting to do. So fast forward, moved to Colorado in 2014, and started Colorado Earth just about 2 or 3 years later. Found dirt, got machines and started making blocks, and built our first house in 2018. So that's the story.
That's quite a journey.
Yeah.
Congratulations. Yeah.
Yeah, thanks for letting me
Yeah, and
pass
I'd
it.
heard so much about all the earth building in New Zealand. You know, I originally got interested in that when I was in college. That was back in 1999.
Mhm.
And I had applied for a Watson Fellowship to travel the world and basically connect with all the famous natural builders in the world. And so I had contacted all these people. I remember there was a character named Graham something or other, Graham North, I think it was.
Yeah, yep.
Anyway, yeah, lots of good earth building going on in New Zealand, and very, you know, conventional looking buildings that are made out of Adobe, and so yeah, some really good codes and information and research coming out of that part of the world. What a great journey. And I mean, it's inspiring for people who are, you know, just getting into natural building to hear your story and hear, you know, how you got to this point, because we need more people like you, Lisa. It's great. You know, it's really a process, and you and I have both seen over the last 20 years, it's such a process to continually educate the public and, you know, dispel myths about earthen building in particular, and, you know, point back to the ancient past, and show even the future potential of earthen building through some of the research that's going on now. I mean, you look at a lot of people in Germany are doing some really cutting edge stuff. You know, you have Block Research Group in Switzerland. There's a lot of really cutting edge research happening right now, and there's just so much potential for using this ancient material in new ways that are efficient, more effective. You know, so ongoing process of education, and I know that's what you're doing now with Colorado Earth. It's kind of just promoting the material, promoting the design aspects that come with the earth blocks, and really just educating people so they can understand what they're buying, right? You know, what they could have. And so, especially in a place like Colorado, I think it's clearly a very fitting environment for thermal mass. You know, a lot of passive solar homes there, obviously. New Mexico, Colorado, Arizona, that area is prime time. Maybe you can go into a little bit about, you know, some of your latest designs and talk to us about the design process that you go through and how you educate your, you know, customers, I guess, with, you know, thermal mass and building science and the energy efficiencies, the insulation qualities of the earthen building wall systems, and maybe just talk a little bit about the most common wall systems that you use also.
Sure. Yeah, well, I mean, coming from a background in New Zealand where it's pretty temperate climate, you know, it doesn't really kind of get into the freezing temperatures very often in the North Island. I never had to really think about insulation, right? The thermal mass was doing that work for us. And the way thermal mass really does work best is when the temperatures outside are going above and below our thermal comfort level, which is around 68 degrees or so. So as long as like most temperatures are kind of going above and below, and it's kind of like having that diurnal effect where it's changing throughout the day and throughout the night, then the walls will stay pretty comfortable. We know historically these walls have done very well in very hot climates. So, you know, I wrote a book, Adobe Homes for All Climates, right? And I probably didn't really do justification to the cold climate. I did talk about the double wall system, but I had never done one before coming to Colorado. So it was an iterative process in a way, because the machine that I was working with when I first was in Colorado was making bricks that were 10 inches by 14 inches. Big suckers, right? 40 pounds each. And so the wall needs to be around 10 inches minimum-ish, and it depends on the size.
Isn't that the standard Adobe brick size for American Adobe bricks?
Yeah, it is. It is 10 by 14. Yeah, in New Zealand, we were making about 11 1/4 by 11 1/4, so almost foot by foot square blocks.
Square.
So square blocks, yeah, some with holes and U's and accommodate reinforcing. So the 10 by 14 bricks I was building with, we would design as a 10-inch wide wall, and we put insulation board to the outside. So the main practice around coupling thermal mass and thermal insulation together is that your mass wants to be on the inside and your insulation on the outside. Our value of the insulation is basically resisting that cold as much as it can before it's kind of coming in. So that was the wall system we started with in 2018, a 10-inch wide wall with a rock wool insulation board attached to the wall, using big 4-inch, driven nails, followed with mesh and vapor barrier, drainage mat,
Yes.
layer and layer and layer. And then the
like stick pins, right? They call them.
Yeah, right. Well, everything to kind of protect, to get ready for the final coat, final finish, which is the stucco.
Yeah.
We kind of called for a lime plaster, but the owners ended up doing a cement stucco, which is fine. The vapor is kind of being able to breathe, inside. The rock wool is breathable, so it's still kind of working. So that was, and I said, heck, I'm going to sit here. I'm going to be in Colorado designing these type of wall systems. I really want to know that this is going to be a comfortable, thermally comfortable home. So during the construction process, I actually hired a building scientist and identified these sensors that we eventually installed into the bricks as the wall was going up. So we found locations in the home on the west side and south side, and put these sensors like in the brick. So one towards the inside of the building, one towards the outside of the building, and sensors outside. Anyway, we collected data for about 1.5 years on temperatures. And I have some graphs, that we can show on that. But basically, the wall, the inside of the house stays at 68 degrees during the summer, with no mechanical cooling. And so great, we know that these walls perform well. Thermal mass really kind of keeps that heat outside. It stabilizes the internal temperature. And so we checked the box on summer performance, but it was really the winter performance that I wanted to see. And we purposely put one of the sensors behind their wood burning fireplace, which they were they loved, building with these wood burning fireplaces. That was their primary source of heat. We did have some mini splits designed and installed in the home, but they rarely use them or really turn them on because they do have their fireplace as the main heat source. Right. So anyway, we could see in the sensors as the wall heats up when they build a fire. So we were actually able to see when they built fires, right? And then we could see the thermal lag of that heat being stored in that block, over around 14 hours. The house also stayed at 68 degrees steadily throughout the winter. Again, no mechanical cooling, no mechanical heating, with the use of their fireplace. So, and they also had we designed for great solar gain. We had some clear story windows facing south, a lot of solar gain, southern exposure. So I felt very confident about moving forward with thermal insulation and thermal mass. And the study, which you can find the study on my website at Colorado Earth, then it summarizes that this wall system would be very good in locations like schools or churches or offices where everyone's coming in at the same time, because the thermal mass is able to absorb some of that body heat, excess human heat generated from us, and store it and keep temperatures very stable, rather than a mechanical device kicking on to start regulating the temperature. So that was encouraging. And it also said that this wall system would be good in a power outage. you know, when the power is out, the mass is actually able to retain for a long period of time and keep comfortable temperatures. So that, anyway, that was both very encouraging. I mentioned it was been a kind of iterative process, and so 40-pound bricks are pretty heavy.
Yeah,
and I also didn't love the having to put on the mesh and the vapor barrier and kind of all these layers, right? There's something beautiful and simplistic about just the earthen walls themselves. And so I got a new machine that made 6 by 12 bricks, 6 inches by 12 inches. So if my hands, not everyone can see them, but if my hands were bricks, I'm building now a wall that's 6 inches and 6 inches on the outside and inside, and a 3-inch gap between. So a 15-inch wide total wall, 3 inches between for a cavity for insulation. So like blown in or loose fill, cellulose, or perlite. There's other types of loose fill insulation, but those are two of the more common ones, cellulose being a little bit higher R. So this wall system is now the double wall system that I'm building with exclusively in Colorado and in other locations. There's a energy code that we have to comply with, and this is probably where I'll start talking about the energy code, unless there was something that you wanted me to back up on.
No, I mean, it's all great stuff. I can
Yeah.
I'm trying not to interrupt you. I got plenty I could say. Just to,
yeah,
over my experience, lots of time I do mostly research and like experimental things that don't actually meet the code. A lot of my projects are just beyond the codes, but the beauty is, you know, you're able to build this wall system in most locations in the US. And I think, you know, also we want, you know, we need cold climate systems. So it's like, we want this building to stay warm. When we're in there, we want it to be able to resist the weather outside when it's -20, which can happen. And so, yeah, I think the 3 inches of perlite is a good move. I wonder if you could even, you know, modulate the same type of wall system and achieve that with a 6-inch gap between the two layers of bricks for other climates.
Yeah, I mean, certainly. And I think that it's really about what the code requires through the energy compliance and the HERS rating. There's a certain, I'm going to get to the kind of performance code part. Also thermal comfort and the expectations from the clients and the builders, and also what other heat sources are there available. And I'll talk about how thermal mass kind of works in general in cold climates. So the energy code, you know, was developed for good reason to have more energy efficient homes. For me, what it's lacking is an ability to interpret thermal mass and how thermal mass behaves. And it's challenging because the computer models and simulations that we work with don't have the ability to input and output thermal mass, right? Because it's a very dynamic situation. It's not a static environment, like kind of how we test the R values. So that being said, there are 3 different ways that you can get through the energy code process. They're in the very most common way, if not, you know, the only ways that most people know about is the prescriptive method. And that is saying your walls need to be R this, your roof needs to be R this, check the box for every assembly piece and make sure that they are all meeting a certain R value minimum. That's the prescriptive method. And that's not the method that I use. So I have to educate folks on the performance method, which looks at the building envelope as a whole system working together. And it is, in essence, kind of making some trade-offs. Okay, if your walls are this, then your roof needs to be this, and it's understanding kind of how heat moves and the whole assembly. So I have, and the third method is as a computer model, a simulated model, which I've never had to go that route, but I have always had to go the performance map route.
Yeah. So you need data from a year at least.
No,
Not necessarily.
no, not at all. It's really just, again, it's the same energy rater that does the prescriptive method can do the performance method. They just have to look at the assemblies again as kind of a holistic process. And I have another white paper on my website if people want to see from Energy Logic how this was done. And that paper was written for a house that we designed in Steamboat Springs, Colorado, climate zone 7, 9,000 feet elevation, cold, snowy. And we got through the performance method through that 3-inch cavity of insulation. We thought that we might need to go 4 inches, but we didn't need to for compliance. So that's kind of one aspect of the compliance is that energy code and the HERS rating and that process. The other is just around, you know, people's expectations of how they're going to be comfortable in this home. And so that's when we look at their heat sources and, you know, radiant and geothermal or mini splits or fireplaces, you know, masonry heaters. I've never put in any ductwork in my houses, and I hope I never do. I hope I never have to put in forced air. I don't think it's healthy. I don't like the heat, how it feels in general. And ductwork is dirty, right? So
it takes up space.
It takes up space. Funny, one of my clients came to me because she just didn't want to clean the vents anymore around her. You know, she wanted a ductless home. So anyway, that led her to find me. That was actually the first house we did in Colorado. The father of that husband of that house, same house, was a firefighter, and he wanted a house that didn't burn down. So that's another great aspect of the blocks is that they are unfired in the production. So when firing them, they become stronger. They actually turn into the face of it against fire for 8 hours turns into a fired face. When I say that, just the first ½ inch of the block,
like a terracotta,
turns terracotta. And again, this is going to test after 8 hours of it being in a furnace.
Sure.
So pretty cool in that regard, especially as we look at the wildfire rise and our vulnerability to wildfire.
Yeah, that's huge. I mean, this is maybe the biggest selling point there is right now for most people is, you know, would you like to invest a lot in your home and have it burn down? Probably not. You want something that's going to endure over time, at least. Even if the roof were to be destroyed, the roof could be rebuilt on adobe walls that remain.
Yeah, right. Protecting our belongings and making it a safe place to evacuate from. You know, I mean, I'm helping. We had a devastation Marshall Fire here in Colorado at the end of 2021 in December, and 1,000 people lost their homes. You know, there's been a lot of rebuilding efforts starting to happen now. So I've got a permit just was accepted for our first Marshall Fire rebuild in a track home neighborhood redevelopment or development project. So we're excited to have this family get back in their home, and they chose earth blocks because of the fireproof. But not only that, a lot of these families were in their house as it was on fire, and so the fire was spread by strong winds that day. We have strong winds often in Colorado here, and so there's also an element of protection from sturdy, heavy mass walls, right? You don't hear the wind, you don't feel the wind, and gives a greater sense of protection. A lot of my clients talk about the safety that they feel. They even say, hey, there could be an Armageddon going on outside and I wouldn't know about it.
Yeah, I agree.
Yeah, so that's really that's awesome to kind of give that sense of mental security as well as physical security in an event of wildfire. Acoustics, there's been acoustics testing done that the comparatively to a timber frame house, the acoustics are about half of the sound damp proofing. So anyway, a train outside, you'll hear it half as loud, which in the acoustic world is quite a bit.
Yeah, yeah. I mean, if all those people out there listening who haven't stood next to an adobe wall, I mean, go find one and stand next to it, and you can realize pretty quickly that you can't hear your friends on the other side of the wall, even
Right.
if it's not an enclosure. It just blocks sound so effectively, and the
Right.
thicker the wall, the better it blocks the sound. But it's the density of the sand in there, it will block everything. All the sound just bounces right back.
Yes, that's right. So anyway, that's a good way to talk about the thermal mass and the insulation, thermal comfort. It's a lot of what I'm working on here. Cold climates and passive house, and like these are the wall systems that have made really great headway in cold climates because they are very energy efficient. And these assemblies are very tight, and the ventilation system allows that environment to stay at a healthy rate for us as humans. What I'm also aware of as I look at the problems that the buildings are trying to solve is in the use of our resources, and whether or not climate change or carbon or some of these things are of concern to everybody. I think it still makes sense that we're using our resources wisely. And so looking at local materials and local supply, natural resources that are really, I'm using a waste product from the quarry. They are screening and excavating out granite and aggregate and chucking the stuff that I love back in the hole or off in a pile that I acquire. So, it's really about, diversifying the resources that we use and using a more natural material and less waste. And so I'm currently conducting a life cycle assessment of the production of the blocks, calculating every little gallon of petrol that goes into the skid steer and the machines that I use.
Sure.
And so to really kind of give that nutrition label of what type of imprint am I making comparatively to other materials like concrete blocks or fired bricks, for instance, as well. So more data is important, as that we're informed on making decisions, if those are the things that indeed the policymakers are helping to work us towards.
Yeah, and the customers, I mean, they can research and look at the numbers themselves for, how much energy is embodied in this material versus another material. Right. And your sand and your clay are both coming from very close by where you're making the blocks. And it just makes sense in general. I mean, if you want to make money, you want those materials to come from nearby. So it just makes common sense. I mean, instead of the rest of the world is busy shipping really big heavy things like all across the world back and forth, because they're made over here and they're needed over here. And you have this product that is directly applicable nearby, and the materials come from right there. It's really like a beautiful thing to see that happening. And so you're stabilizing a little bit with cement, I assume? Not
anymore. Okay. I've been like kind of my whole adobe career in New Zealand, Portland cement stabilized. I only had done one lime stabilized house for a client that preferred lime, and have been using Portland up into last year when I switched to lime. So I'm doing fully lime stabilized blocks. Again, I see it as a lower embodied carbon product. I see it as a more healthier product. And with the life cycle assessment I'm doing, want that to be the baseline, a baseline for me. I think that there's still room for me to improve as I collaborate and work with other, industries and waste products, and on incorporating other materials that can improve the potentially the performance without needing the Portland or the lime.
Yeah.
I'm actually currently have a grant. I'm a participant in a grant with the National Renewable Energy Lab here in Golden, and so we're looking
Congrats.
at yeah, thanks. So we're looking at a waste material from an industry that could potentially replace the use of Portland. So I think, there's a lot of people in this space right now exploring bio binders and the like, more resourceful replacements for Portland cement.
Sure.
So I'm really excited to be in that space, and hopefully, again, I think that I would like to think that the mixed design could just continually to be improved and modified and adjusted based on various locations and based on what's really readily available. So it's exciting. It's exciting to think that, our characterization abilities of different materials can lead us towards a variety of mixed designs. It keeps us really nimble, as we're able to make blocks that really just achieve a certain compressive strength and modulus of rupture. Those are the two requirements needed for, the engineering side of the material. So yeah, excited about that. But yeah, I'm
great summary. Yeah, I mean, and just for the audience, we've talked about this before, but my work going back for the last 20 years has been mostly in pure Adobe. So I've been somewhat anti-stabilization for the purpose of proving to everybody, to educate them that it's possible to create very durable, structurally sound buildings with pure Adobe without stabilization. But when you get into the building codes and, like you said, the modulus of rupture, having that little bit of lime or Portland, I think it's essential. And then you're also compressing the material pretty intensely, right? It's a gas powered machine, and it hydraulically compresses them.
Correct. Yeah. It hydraulically compresses all the air out into a much more dense, packed Adobe brick, right? And so, Adobes have to reach a minimum compressive strength of 300 psi, and the compressor blocks that I'm making also structurally need to meet a minimum of 300 psi. But the Adobes are around, stabilized Adobe might be like 500, maybe 600. Stabilized compressor blocks are around 1,800, 1,500, 1,800. It's no big deal. It's no big deal. We don't really care about compressive strength. It's just muscle flexing, really, when it comes down to.
Yeah, you could build a 15-story building out of those blocks.
Yeah. But the main reason why I stabilize, and I'm very respectful of the fact that of people that don't, I am wanting to protect those walls during construction. I don't know if the walls are going to go half up and then be abandoned due to construction delay or whatnot. And I don't know. I'm trying to protect them before they get their plaster coat on them. So I'm also in a freeze thaw environment, which is different, and and I'm also transporting blocks on flatbed trucks, across on bumpy roads. Anyway, I'm trying to give them as much of a chance of survival and kind of integrity, rather, is a better word, before they get their kind of final skin and final protection on them, which is what I believe most of all Adobes need in most climates. So that's and I'm trying to, it's a very small percentage of around 4 to 6% by volume. Sorry, by weight. Volume is a different number because there's a different weight metric there. So but again, I'm excited about the life cycle assessment so that I know exactly the impact of that stabilizer.
Only 4% lime.
Yeah.
Oh, that's incredibly small. That's amazing.
Yeah.
And then with the compressive strength that you're getting, it's like, you can accomplish a lot of things, and you're making the 6-inch wide bricks, and so you're also dabbling with domes and vaults, right?
I am what's the right word? I'm putting it on the menu. I am talking about domes, masonry as an art form. And so I myself am not a dome builder, but I fortunate to know dome builders and very highly skilled bovaderos, people that build the bovedas, the ceiling treatments out of masonry. It is typically done out of a low fired brick, but it can be done with even earth blocks. So just again, kind of really celebrating masonry and kind of what, I think there's other benefits to the domes and vaults with regards to structural strength, but also that fireproof piece of it too, because the roof is the most vulnerable, place where the smoke comes in the vents and kind of lifts and has the trusses or rafters on fire. So excited about introducing or letting people know about masonry vaults and domes, for sure.
Yeah, it's a beautiful thing. It's one of my main areas of interest. But yeah, I think we covered most of the things. There's also the aspect of the longevity. I mean, these earthen materials, the compressed earth block, my understanding is it can last hundreds of years longer than a cement block. Can you speak to that at all?
I don't know about any data on the cement. I mean, it's mainly, a CMU, a concrete masonry unit, is primarily sand and Portland, right? So I think what my concern and the industry's concern is that we're running out of enough aggregate and to make CMUs. Like, we're just running out of some resources. And Portland is what makes concrete, right? So Portland cement is one of the highest embodied energy materials, and that contributes to greenhouse gas emissions today. And that's getting that industry is getting a lot of pressure right now because of its impact, and because there's a real sand war going on out there.
Yeah, we reached peak sand, I guess.
Yeah, it's getting very difficult to find virgin perfect coarse sand that we need to kind of for construction. So we might get forced into looking into other options, and adobe and earth blocks and natural building is certainly right here ready to pick up some slack, and hopefully kind of make some better impacts. But in terms of longevity, I mean, there's been, Yemen is known as the Manhattan of mud. It's got 12 or 20 story buildings that have been in constant use for over 1,000 years. There's just lots of examples around the world where these structures are standing for thousands of years. So, I don't know what the longest concrete building is or whatnot, but
I don't know either. My impression of it was that, especially with the presence of water, your typical like poured Portland cement foundation, especially touching the ground, getting water into the little cracks. There's always cracks, and you get frost heaving and so on. That aspect can usually last between like 100 and 150 years with good service, and that's it. So I think there is a lot of space for a lot of new materials, or using materials in different ways, and the compressed earth blocks and various systems fit into what might be considered a longer term approach. Because if you look at some of the most ancient buildings, they're built out of adobe. Obviously, it can, although people think, oh, it'll wash away, it can actually withstand, even unstabilized adobe can withstand millions of cycles of water absorption and water escaping it. So it's a different animal. It's different than cement. It doesn't have that sort of it's not relying completely on that chemical to hold the sand together. It's the clay itself that is doing a lot of the work, and clay is very durable stuff.
Mm-hmm. Yeah.
So there's that, but and then there's the health aspects as well. We didn't touch on that yet. So, you know, the breathability of the walls. This is usually the main goal of my clients is they want something that's beautiful and healthy, non-toxic. You know, it's a very common thing. People are allergic to a lot of the toxic chemicals these days, and so they want walls that breathe and have just clay and sand, pure clay and sand. It's a common thing. So I'm sure that what you're building is going to be far beyond, by leaps and bounds, healthy compared to, you know, your typical track homes where they have like vinyls and VOCs and these types of things. I mean, what's your experience with this topic?
Yeah, exactly. I mean, I think I'm getting a lot more people coming to me that have these sensitivities, and it's pretty devastating, their stories, you know, of how their mold allergies particularly have affected their lives, to the point where some are living in their car, and, you know, some have lost a baby they were carrying, you know, just really devastating situations where their health has just impacted their life, being sick in their home. So I'm seeing this more, and these people are just really, really needing healthy homes, and it's hard for them to find, you know, people that can help them. I'm also learning that it's very individualistic, and that it's hard to also know what is going to make somebody feel healthy in them, or I'm learning this until they maybe just, you know, spend a couple hours inside of a building, and then they kind of can identify if they feel good or not. So, you know, but the line that I'm working with has a pH in which mold cannot grow. So that would not be a problem. And then also the relative humidity of these homes is around 40%, which is optimal for human health. So yeah, I think there's a, you know, we all, you know, really benefit from healthy environments, and from, you know, architecturally, and just the quality that the ambience and the energy really that these walls put out, right? So I'm excited to help that large and unfortunately growing community that need healthy places to live. Yeah. So
yeah, it's a huge one.
Space right now, trying to help people. There's some people looking at, and there's a lot of them are looking at the healthy homes of this material, using this material.
Right. Yeah, and it reminds me of in the last year or two, my latest direction of study is into bioarchitecture, working with Dan Winter, who's a genius electrical engineer and mentor and friend. And basically, what we've come up with so far is that we can measure the life force energy, the capacitance, the electrical capacitance inside of architecture, and you know, repeatably measurable with scientific instrumentation. And buildings that have a lot of steel or aluminum or you know, certain other materials, they can really destroy the life force energy. So that would mean that you try to grow some plants in this building and they'll die. You try to raise children in such a building and their brains won't develop properly. And so this is something we can now point to and say, okay, these architects are making life-giving buildings and these ones aren't. So there's just kind of this line in the sand, I think, that's being drawn. And so my takeaway is to move away from steel and aluminum and just continue promoting the earthen wall systems for this reason, and explain to everybody why. I think people are kind of skeptical. They think it's you know, something woo-woo at first, until I start showing them the data I can show them, the antenna that I have to use to measure this capacitance, and we correlate the measurements with also plant growth and plant seed germination rates. So there's a lot of interesting stuff on the horizon here. This is the leading edge, and I think that anybody who really did their homework and looked at the data and was very serious about their health would consider this stuff, and then hopefully they'll be calling you and asking you for a home because of this.
Yeah, cool. Awesome.
But I don't know how much rebar you have to use, to meet the structural requirements.
Yeah, it varies depending on the seismic risk, wind load and wind loads. But not much, right? They're vertical bars going in every 4 to 6 feet on center, maybe.
Just a little bit to give it that little extra.
Well, these walls are not very ductile, right? So, meaning they don't bend really.
Not flexible.
Yes. Not flexible. Yeah. And so the risk for them is in shear when they're being shaken by a seismic event, right? Or very strong winds. So the rebar is there to kind of really help some of the ductility and kind of strengthen them. So in an event, in a seismic event especially, these walls are heavy and brittle, and unfortunately they've been built improperly without even, a bond beam is probably the most important structural element, which is a continuous cap around the top of the wall, often formed in concrete, or it can be timber. But it needs to be continuous, and it needs to span the entire wall, and it needs to go around the entire top of the wall. And a lot of these homes, are built in areas of the world that are not engineered, and so in a seismic event, the walls are heavy and brittle, and they fall and they hurt people, and it's gotten some unfortunate bad, stigma, right, for that purpose. So
but it's poor design and possibly poor craftsmanship.
So they've, and often in some areas they've outlawed, the use of it, right? Because there's not the institutional knowledge of how to build with bond beams and reinforcing. And, in locations and areas of the world where they don't have access to rebar, another good method is a cage. So building kind of like a cage around the material to contain it, like with just, even just fencing or fabric fencing. Yeah, or like a fabric fencing, and then you could plaster that. Anyway, you want something just to contain the material to allow you to get out safely in a seismic event.
Sure.
So those are things that are being done in like South America, but here where we do have access to rebar, vertical reinforcing with concrete grouted cores is what we engineer these walls as reinforced masonry wall system. So that's
it's more expensive, but you have the option now of the basalt roving rebar that's made of minerals, and it's equally strong to the steel. I haven't got to play with that stuff much yet, but it seems promising.
Yeah, I've worked with basalt mesh, which is pretty cool stuff. It's kind of like more fabric-y and more woven, and like you said, doesn't rust. So
right, and doesn't rust, even better.
Yeah.
That's huge, actually.
Right.
Yeah. And then I've also seen some, there was some research done years ago. I'm trying to remember who these people were, but anyway, they built a model of a cob home. So this is a continuous puddled adobe style. So there's no bricks, there's no brick joints. It's continuous, and there's straw inside the earthen masonry going every direction, and they built the whole building. They put it on a shake platform to simulate a seismic event, and they got that thing up to, like a 9.5 earthquake or something, and it didn't fall down. It cracked. It severely cracked, but it never fell in or anything dangerous like that. So I think part of the issue that we're facing right now is also just, yeah, just a stigma and kind of a misunderstanding and just a lack of knowledge, really, lack of education.
Yeah.
There's a lot of ways we can go about fixing the problem.
Yep, you're very true.
But yeah, so tell us, people can go to coloradoearth.com, is it? And they can get in touch with you and do some design work with your team.
Yeah, for sure. Yeah, you can talk to me if you want. You can book a time to talk with me and ask questions. I give some free time for that, and if you want to look at the resources page, I have a lot of technical papers and white papers, some of the energy performance stuff that I talked about today, and the energy compliance performance method that I mentioned. There's some, there's acoustic studies that I can point people to from the University of Oklahoma. Energy efficiency studies also from the University of Oklahoma. So there's a lot of good technical information that should be helpful. And then I do help people with the design and engineering and getting them through the building permit process. I've never been turned down for a building permit, and I've never built in California, but there are permitted adobes getting underway now in California. So there's a great organization, Adobe in Action, and Adobe is now software that is working to get Adobe's back built in under permit in California, so reinforced and all that good stuff. So and I guess I'm headed to San Diego at the end of this, in a week or two, to talk about wildfire resilient structures, and this is certainly a building product that can resist wildfire. So looking forward to kind of bringing up this building product as something that we can utilize more often as a rebuilding material. So yeah, that's where you can find me at Colorado Earth, and I've got some videos on YouTube too that you can check out, and Instagram and all that good stuff.
Yeah, and your book, what was it called? Adobe House for All Climates.
Close, yeah, Adobe Homes for All Climates. So you might even be able to still find it at the library and things like that. I'm working on a second edition of it, or a version of it, to incorporate the Colorado double wall and the kind of some of the thermal performance results that I have of it. But that book mainly was written on my experience in New Zealand. So you'll see, the New Zealand bricks and how to make bricks, how to stack them, plaster them, do lintels over the doors, arches. It's a great how-to manual for interested builders. And the compressed earth block is very transferable to the Adobe construction knowledge. So it's just that we compress the machine in a block and compress the material in a machine rather than form them in a mold.
Yeah, same type of blocks. They're just a lot stronger.
Yeah, a lot less water in the compressed earth blocks.
3 times stronger.
Probably 3 times stronger. Yeah, 3 times higher compressive strength. But again, the bottom brick and the first course of the wall, the very bottom brick of a house, is taking on about 7 pounds per inch of pressure. So that weight is just being distributed through the wall. So that's why I say, the compressive strength is really in transportation of the block, and so that if you drop it, it doesn't break into a million pieces. You're really using the mass of it together to build a very strong structural wall that's supporting the roof and everything above it. So yeah.
Well, yeah, you're such a leader in this field, and I learn a lot from you even after I've been studying this for so many years. So thank you for your dedication and just such a wonderful and valuable contribution.
Oh man, I feel it. Thank you. Yeah, thank you. Yeah, pretty much love this stuff, and really just thankful for this community too, that supports and encourages one another, and you know, it's difficult in an industry to be misunderstood or an underdog, but I think that there's something that draws me to the product is there's a lot of humility and humbleness in it, yet so much strength and beauty. And I just love sharing that with others. So thanks.
Excellent. Thank you, Lisa.
Yeah, thanks, Scott.
So we'll see you again next time.
Sounds good. Have me again. Chat.
Okay. Talk to you soon.
Yeah. Bye, Scott.
Bye.